All right, we're going to start chapter 3, which is particle equilibrium. And the way the chapters are going to go as we go through the course is typically I'll start a chapter, go through a process of deriving the equations, and then we'll just solve a bunch of problems. So we'll start with that here. So for particle equilibrium, the question is what does it take for, or what does it take for a particle, single particle, to be in equilibrium? Well, it's really simple. The sum of all the forces external must equal 0, which, if that's the case, means the sum of the forces in the x's are 0, sum of the forces in the y is 0, and this is a vector, so in every direction you pick, the sum of the forces on the particle must be 0. If they're not 0, it's accelerating. That means it's moving. That's simple. All right? So given that, we have a couple more equations that will have it available to us. Spring force. All right. Or this is a linear spring. Okay, so picture we'd have something along the lines of this. So here's, say, y. Here's x coming off. So here's a spring attached to a wall. That's the spring. There would be some spring constant associated with that. Okay, I'll put a little handle here, and this is somebody's hand, and they're pulling like this, stretching the spring. And so the displacement from them pulling would be like so. All right? So if you are the person and you pulled the spring back, what would you feel? Well, because of the spring being attached back here, you'd feel the spring force against you. So the person's pulling this way. The person would feel the following. Minus kx, where x is the amount they displace it by, from the unstretched position. Okay? So they would feel the opposite. Now, but if they're doing this, well, then the spring would be wanting to pull on the wall, so what would the wall feel? Well, the wall would feel k times x. The force is proportional to the stretch, or likewise the compression if you were pushing in on the spring. Okay, and the spring just always opposes you, so it pushes in the opposite direction. Okay, so there's that. Next thing, dry friction. This is something that you should have had back in high school. I know you had it in Physics 1081, assuming I remember that number correctly. And so this will just be just a quick review of what that is. So picture we'd have a generic box here. There we are. And suppose somebody applies a force to want to move the box, F, and the box has mass. So the box has weight, mg, and here it is moving along the floor, and the floor is rough. If it's smooth, there'd be no friction, so this is roughness I'm drawing in. Now, the box isn't falling through the floor, so the floor would be pushing back. This is called the normal force. So the normal force would be due to two things. One, the weight coming down, and notice I'm pushing the box, but I have a little bit of a downward force in the box as well, so it's not all horizontal, this force. So the normal force would be opposing the vertical component of the force applied to the box and the weight. So this is, n is a bit more than the weight. And as this thing wants to slide forward, friction would be going, and it would go like so. So there'd be a force of friction going in the other direction. All right. So you should recall then that we have two cases. The static case and the kinetic case. For the static case, okay, that means we're pushing and the box ain't going. All right, the friction is too high, the box isn't able to slide. All right, well, for the static case, the force of friction maximum is μs. So this is the coefficient of static friction. It's a property of the relationship, the material relationship between the box surface and the floor, times n. All right. The larger n is, proportionately, the more friction is available. All right. Now notice I made a point of saying max. We never actually know how much static friction is there. If we are right at the edge of sliding, that's when you would have the maximum friction. But here's the deal. Friction is smart and lazy, okay? So there's only as much friction force here as needed to stop this thing from moving, all right? So friction's like, well, if I project this down and there's only 10 newtons of force going in this direction, it'll only rise up to 10 newtons. Now, μs times n might be 50 newtons. But if I only need 10, that's all it's going to give me. And that makes sense because this is the maximum available. If 50 was available, it wouldn't make sense if you tried to push this forward with 10 newtons and it gave you the maximum available friction and said, let's make the box go backwards all of a sudden. And basically push you over. Okay? From the static point of view, there's only as much friction as you need to stop it from moving up to this limit. Okay? That's the critical point here. And you've had this before. Now in the kinetic case, it is moving. So in that case, we exactly know what the friction is. The force of friction is μk times n. So if it's moving, find the normal force, multiply by uk, and you know the exact friction force working against you. Now, until we get into the dynamics part of the course, that ain't happening, okay? So we don't have to worry about that too terribly much. And it makes sense that μk is always going to be less than μs. So because this is the maximum it can be before it starts to slide, all right? You can't have more friction, suddenly have, μk couldn't be bigger, so once it starts to slide, there's suddenly more friction there, because then it would stop. So it must be the case that μk is always less than μs. And there you have it. All right. So now we're going to start our problems. So I'm going to stop this video right here and set up for our next two problems. See you in a moment.